So this is week 9 lecture for remote sensing, and we're going to talk about some of the more interesting aspects of what we can figure out uh, by looking at multispectral electromagnetic radiation. So let's go back again and talk a little bit about this idea of electromagnetic energy and what it means. You've got this magnetic field. We measure it in terms of a couple of things: the wavelength, which is the distance between the peaks in the wave, and frequency, which is how many peaks come by a certain um, space in a given amount of time, and that is limited to the speed of light. So this is a diagram you've seen before, and we're looking at the amount of energy that is released by various things. And you can see at the top we have the energy released from the sun, and it covers a wide spectrum of electromagnetic energy. The frequencies range from the very, very short to the extremely long. And in the middle, where those two lines are, that is the visible spectrum of light. That's what we can see. But that's not the only sources of light. The only sources of energy. The Earth itself does produce a certain amount of energy. And you can see that it is a much longer wavelength, and it is outside of the visible spectrum. But when we look at the next graph down, in terms of transmission, and when we look at the transmission graph, we're talking about the energy passing through things. And for the most part, we're talking about the atmosphere. So energy from the sun coming down, or energy from the Earth going up, meets some degree of impedance by what's in the atmosphere, whether it's the magnetic fields, or the ionosphere, or particles of dust, or water vapor, or CO2, or ozone, or any number of things. They can all interfere with the path of this energy. So as we look at how these two charts, these two figures compare to one another, I want to point out that as you see those two lines in the top where the visible spectrum is, if you look below, you notice that there is a large hump in the transmission. So to read this table, the further down the red comes, the less energy is transmitted through the atmosphere. The higher up the white goes, the higher, the lesser amount of energy that is inhibited during this process. In other words, it allows it to be transmitted more fully. So when we get into that visible spectrum, not much blocking it, comes right through. And as we go up, you'll see that there are various peaks and valleys and areas. Like, for example, there over 100 micrometers, there's an area where there's no transmission. And there's other areas, like in between, like they're around 10 micrometers, where there is some transmission. And areas, for example, at 10, 9, 8, 7, so they're around 6, there's none. When you get there around 3 or 4, you have some again. And what this is showing you, or what this is intended to show you, is there are different spots in the spectrum where energy comes through. Those are the only spots where we can effectively look at things from satellites. If the energy doesn't make it through the atmosphere, we can't make any use of that for our purposes. So how does this various windows in the atmosphere where energy comes through relate to various things? Let's compare what we have here at the bottom. Different sources or means of how we could measure or interpret that energy. Starting with the human eye visible spectrum, that's pretty much what we have. Photography, we can go down into the ultraviolet, we can go up into the infrared. Thermal scanners, they're a little further along, a little bit longer frequency. They measure thermal infrared. And then we have multispectral scanners that can literally read anything from down to the lower end of the ultraviolet up into the extent of the thermal infrareds. We also have other means like radar and passive microwaves as well that are further out. But thinking about this should make you understand that regardless of what and how things react to certain forms of electromagnetic energy, if that energy isn't in one of these windows where it can make it through the atmosphere with little inhibition of the transmission, it's not going to be useful for what we're doing. And that leads us to the next part, which is the idea of spectral signatures. And we've talked about them before a little bit, but we're going to go over it again. Signature implies a unique spectral relationship, and that is not always the case. Biogeochemical signatures, in other words, minerals or nitrogen in plants or things like that, we can identify a lot of that stuff from hyperspectral data, but it's not an absolute, always easy to identify thing. And there's lots of reasons, but the main reason is is the visibility or the variability within those signatures and what causes that variability. Well, for one, the spectra are not unique. There are other things that have the same sort of signature. There are changes in illumination. There's just natural variation in the composition. For example, if you're looking at how a particular leaf might respond, different kind of plants, different kind of leaves. Or it might be different kind of leaves within the same kind of plant, or it may vary from plant to plant. You can also have the effect of mixed pixels, where if you know that the absolute pixel size that you're looking at on the ground, for an object to be cleanly identified in an individual pixel, it has to be at least, generally speaking, twice the size. To be real comfortable, I would say 4 times. And then there's just noise, static, errors, dust on the lens, if you will, if you think of it like a camera. Anything that can creep in and cause problems to your information. So let's take a look at a spectral reflectance graph for vegetation. So as we go along the x-axis, we have the wavelength of the electromagnetic frequency, and along the y-axis we have the percent reflectance. Now again, remember what reflectance is. This is the percent of the energy of incidence. In other words, the amount of the energy that is directed upon an object. When it's directed upon an object, it has 3 options. It can go through it, it can be absorbed by it, or it can be reflected from it. So we're just measuring how much of that is reflected. And again, 4 to 7, visible, near infrared, shortwave infrared, etc. There you can see the blue, green, and the red. And here is what vegetation looks like. Has some reflectance in the visible, but mostly it's absorbing it. Has more reflectance in the near infrared, less as we move through and towards the shortwave infrareds. So what does all this mean? Well, our satellites that we have in space that collect this information for us often collect the information in what we call bands. And bands are not a single frequency, but it's a range of frequencies. So it might be, for example, from 0.4 to 0.5, from 0.5 to 0.6, and then maybe it's from 0.7 to 0.8, or something like that. Here you can see that in the IKONOS satellite, there are 4 different bands that we're looking at here, and you can see the frequencies where they range from. That there's a gap between band 2 and band 3, and there's a gap between band 3 and band 4. Bands 1 and bands 2 basically touch one another. and they go from the visible all the way up into the near infrared. So there you go. 3 bands in the visible, 1 in the near infrared. Different things in the atmosphere can interfere with this. One of the big ones is water. Same kind of graph, wavelengths across the bottom, percent transmittance on top. So the way you look at this and read it is, the higher the percent transmittance, that means the more energy that gets through. Alright? Because when energy, electromagnetic energy, hits the water molecules in the atmosphere, if we have a value of 1, that's 100%, that means that it sails right through without any problem. As we get into moving from basically from point 4 to the right, and we get over closer to point 7, you'll begin to see how we start having some less transmittance, and our transmittance drops down to around 0.8, and that is because as we're getting further and further towards the shortwave, we begin to see the atmospheric water vapor blocking the transmittance of the energy. Similarly, same setup, CO2, 100% transmittance is there at the 1 value. We'll go across that line. Carbon dioxide doesn't bother anything until you get over around 1.5, and then there's some areas there where it starts to impact a little bit, but when you get up around 2, you really have some big drops. And these are places where you can't measure effectively as much or as well those frequencies, because the CO2 in the atmosphere will not allow the signal to go through. So let's look at some of these trace gases and how they respond. So you know from your high school biology classes that most of the atmosphere is nitrogen, but there's also some oxygen and some carbon dioxide and other things. So let's look at what some of those other things are, including oxygen. And you can see that there are some locations where oxygen inhibits the transmittance. There are some locations where methane does, where nitrous oxide does, where carbon monoxide does, as well as ozone. The key thing to remember about ozone is, why is it important for us? Blocks out the UV. What does the UV do? Gives you skin cancer. So let's look at a summary of the transmitted solar illumination. So the solar illumination peaks are all in the visible spectrum. The major absorption features that we have to deal with are water at 1.4, 1.9, and 2.6, CO2 at 2, ozone at 0.3, and then some of the trace gases. And so as you look at this graph, wavelengths across the bottom, solar radiation values on the y-axis. And basically, the further down the line is, the less energy that gets through. And so anything that's in the ranges where you have those deep dips, it's going to be very difficult to measure from space. Alright, so let's go back and try to combine all this together into sort of one cohesive idea. Let's look at that spectral reflectance again of vegetation. So this graph has a lot going on. The first thing we're going to look at across the bottom on the x-axis is the wavelength. And you can see where the visible spectrum is, where the reflected infrared is, and then they've broken that down into the near and the middle infrareds. The visible is also broken down further into the blue, the green, and the red. Alright. Now, the line that goes across the middle of the graph that is the reflectance signature of the vegetation. Looking at the y-axis on the left, this is percent reflectance, okay? So this is how much or what percent of the electromagnetic energy is reflected off of the surface of that object at that wavelength, okay? So if we're thinking about this as a leaf and we're looking at just the visible spectrum, you can see that very little blue is reflected, very little red is reflected, but more green is reflected. What color is vegetation? Green. So that should make sense. Now, why do we have these dips in the blue and the red? It's because those are where the chlorophyll absorption bands are. That's where the chlorophyll that is in the chloroplast in the leaf structure that absorbs sunlight, this is the sunlight they absorb. Alright. I also want to point out the top, you see that it looks like paint runs coming down over the graph. That is the atmospheric transmission in terms of percentage, okay? So when you don't see any of that stuff sticking down, it means there's 100% transmission through the atmosphere. When you see stuff coming down, that's an indication that the atmosphere is blocking some amount. And so if you look back over there near the red, there's a little bump coming down up there where probably only 95% of the energy is getting through. And why is that? Well, the dominant factors that control the reflectance of the leaves are the pigments in the palisades in the mesophyll, the chlorophyll A, B, the beta-carotene. As you move further over, you get a scattering effect in the spongy mesophyll, which is part of the leaf structure, and then as you move further over more, it's the leaf water content. So in the spongy mesophyll, where you start getting some of this scattering, that's what's causing some of this inhibition of the signal, or not the signal, but of the reflectance. And so that's why you see more reflectance. If you look on that y-axis on the left, it goes up to about 40% as opposed to around 10 or 15% back in the visible spectrum. It's because that scattering effect is causing more of it to bounce off. Now, water absorption bands. If you look at the black line that goes left to right, after you get past the red, it goes up, has a little bit of a decline, and then you have a big drop. And then another peak and a big drop, and another peak and a big drop. Each of those drops correspond with an atmospheric water absorption band. That is a segment of the electromagnetic frequency where water in the atmosphere leads to 0% or near 0% transmittance. And so it's impossible to get really a signal. So let's look at some of these a little bit more. We talked about chlorophyll A and B. Absorption spectra of these different things allow you to tease out what's what. For example, you can see where chlorophyll A is or chlorophyll B versus the various beta-carotenes and other things. So let's look at what that means holistically and how we can use that. Because we're not really so much interested probably in going out and looking at the beta-carotene levels in leaves. We're typically looking at leaves as a means of differentiating the type of plant vegetation. So when we look at the pigments in vegetation that is red obviously should look different than vegetation that is green. And so here we have the same basic reflectance versus wavelength graph going from 0.5 over to 2.5. Remember, down there around the 0.5 we're looking at sort of the visible range. Remember that vegetation in its natural state has less in the blue and less in the red, but more in the green as far as reflectance goes. And if you look at the solid line, it spikes there around 0.5, which is in the blue range, or the green range, I'm sorry. And the red vegetation does not. But when you get over closer to 7, where you start to look at the red part of the visible spectrum, all of a sudden the red leaf reflects more and the green leaf does not. And so simply by knowing that and looking at certain frequencies, certain ranges within the frequency, you can easily detect changes in the pigment color of vegetation. Now what if we throw in a whole bunch of these other things? Wow. You can kind of see what the leaf structure does without the pigments and then what each of the individual pigments do. So let's compare the vegetation reflectance to the water absorption. Now, if we think about leaf reflectance, again, this is the energy that is reflected off of the surface of a leaf, and we're looking at percent on the x-axis on the left there. So the higher up it goes, it means the more that energy is coming off the leaf. The lower down it goes, it means the more that is being absorbed. We start off across the visible spectrum, low in the blue, high in the green, low in the red, jumps up in the near infrared, runs across, and then it dips down, comes back up, dips down, comes back up, dips back down. Everywhere that it dips down as it goes to the right, after about 1.2 or so, you get the little valley. And what does the valley correspond to? That is where we have less reflectance because of the water absorption effect that we see in the atmosphere, but we also see it in the leaf structure. And so if the leaf has more water, it's going to have less reflectance because the water absorbs it. So the fact that the leaf or that the water absorption bands impact our ability to use stuff from satellites is a bit of a pain in the butt. But terrestrially, when we're not trying to shoot through miles and miles of atmosphere, when we're flying at a lower level, terrestrially with aircraft or something like that, there's much less of that there to inhibit it, the signal. And it's good because the leaf structure itself has moisture in it, and so we expect a drop at those particular spots where we know we have those moisture bands. Now, if we have plants that are in various states of moisture stress, in other words, some plants are really hard up looking for water, they should have less water content in the leaves. If they have less water content in the leaf, they should, right, have less impact where those water absorption bands occur. So here we have Magnolia grandiflora, which is just a big old magnolia tree. And we look at these different lines representing different levels of moisture status of the plant. And the solid line is 100%. Okay, that means it's got as much water as it possibly needs. When it has 75% relative water level, 50%, 25%, 5%. And you can see clearly as the available water level declines, in other words, not the available water level, as the internal relative water content decreases. And so in other words, so as the vegetation itself dries out, the plant becomes put in moisture stress, and the response at the water absorption bands declines. So you can use these water absorption bands, as a way of determining how stressed plants are during periods of drought. Now, that's not the only thing we can do with multispectral data. We can also look at the type of vegetation. Specifically, a good example is coniferous and deciduous trees. And here we have the same sort of map or table. Across the bottom we have the wavelengths. Across the left x-axis we have the percent reflectance, and we're just looking at how much energy is being reflected from the trees. And as we go from the blue, we get a spike in the green, we get a drop back in the red. Not enough differentiation there really to maybe help you figure out which one is which, but look what happens as we approach the near infrared. They really start to separate out. Why? Because the leaf structures in deciduous trees versus the coniferous trees are very different. Needles versus broad leaves. One is thick, one is thin. And based on that, you would imagine that they would respond differently. And they do. In fact, you can see clearly that the pine trees have less reflectance than the hardwood trees, the deciduous trees. So when we look at the maple, for example, much more light is given off, reflected off of that leaf structure than is from the pine. And so the pine should appear, if it's not reflecting as much, darker, and the maple, if it is reflecting more, should appear brighter. And what do we see? Hardwood trees like aspen, bright red. Needle-bearing trees like black spruce, darker. So, how can we use some of this information? Well, here is some examples. This is the phenological cycles of soybeans and corn in South Carolina. What does all that mean? Well, that has to do with the maturity of the plants and how they grow. And this is in the same sort of area, two very different plants. And we look at when they were planted, how they develop, different stages in that, when they basically fill in the field, and then how they begin to lose their structure, or they begin to die off and basically become dormant as we approach, and then harvest or do whatever we're going to do for that year. And a couple of things here you need to realize is, if you look at when corn hits its peak, when it's growing its most, it's kind of from mid-July to mid-August. In soybeans, it's from mid-August to mid-October. Or mid-July to mid-August is when is when the soybeans are growing. They're filling up. They're around 50% full, and that's literally like the first half of July for the corn. The corn responds much steeper and much faster than the soybean does. And why is that? Corn is a more efficient user of sunlight than soybeans. They like the warmer weather better, so they grow faster when it's hotter, given if there's available moisture, than what the other plants do. When we look at spectral reflectance of vegetation like we had before, remember in the visible light, 0.4 to 0.7, the thing that's controlling a lot of that is the leaf pigments. Okay? The things like the palisades and the mesophyll and the chlorophylls and the beta carotenes and all that stuff, that's what controls whether it's red or it's green or it's blue, and that's what controls whether we reflect red, green, or blue, or absorb red, green, or blue. When we get to the near infrared, that's where the cellular structure scatters the energy. That's why things that have needles versus things that have broad leaves have a very different response in this region. Not a tiny difference, a significant enough difference that it makes it easy to identify which type of structure we're talking about. When we get to the mid-infrared range, that's where we start getting into those water absorption bands at 1.3 and 2.6. Now, it's also important to know about the stages of the plant, because certain plants will be dominant and growing and active certain times of the year, and other times of the year they will not be. So you might know that corn should have a big, for example, should have a lesser, maybe response in the near infrared than maybe soybeans would. Okay, that's very possible. But depending on the time of year you look at it, it may not be the case. So you have to understand not just the remote sensing side of the science of the frequencies, but you need to think about the importance of the properties of the vegetation, how it grows, when it grows, and that kind of stuff as well. We can also look at water, so not just looking at vegetation, but we can learn a lot from remote sensing values of water. And one of the big things we look at when we look at how good a body of water is how much and how easy light penetrates through it, and that's basically related to this concept of turbidity. Turbidity is basically it's how cloudy your water is, for lack of a better way of saying it. And if we look at wavelengths across the bottom, reflectance across the x-axis, and we look at turbid river water, in other words, it's got a lot of suspended solids. So for every liter of water, there's almost 100 milligrams of something that's in suspension, versus clear lake water where that same liter would only have a tenth of that amount, or 10 milligrams. If we look at those things, how they map out, what you see is the clearer water has less reflectance. And the reason it has less reflectance is, without anything in the water to interfere, and as long as you're not up where the water absorption bands are, that energy is going to be transmitted through the water. But the things that are suspended, the suspended solids, they are, importantly, going to either absorb or reflect more of the energy than what the water does itself. They're going to let less of the energy be transmitted through. So the turbid water should have a higher spectral response. In other words, if you have photos of water bodies with the right frequency of electromagnetic radiation, you can look at that and figure out whether that water is more or less clear. So let's look at some true color sea WIFS image from the eastern U.S. on September 30th, 1997. And then we look at the chlorophyll A distribution at the same date. And you see higher concentrations of chlorophyll in the estuaries and immediately along the coast. Why? Because that's where the water is shallower, that's where there's more nutrients being applied, that's where things are growing. What about other things, not just vegetation, not just dirty water? What about snow? Turns out you can analyze snow more than what you might realize. When we look at the wavelengths, when we get down there around the visible spectrum, as you might anticipate, we have nearly 100% reflectance, meaning snow is white. And as we go up in wavelength, that reflectance drops. When we get into the near infrared and up into the other areas, it is much less than 100%. Turns out the crystalline structure of the snow itself, or the effect of they call it grain size, has to do with how these reflectances take place. And so if you look at these different measures of grain size, as the grains get bigger, less is reflected, more is absorbed in that near infrared and other areas. So how could you use this to your advantage? If you have a satellite that collects information between, say, 1 and 1.5, and you have multiple areas of snow, you should be able to classify out different grain sizes of snow in terms of how they respond to those frequencies. And you're saying, well, why does that matter? The Inuit peoples are alleged to have upwards of 100 different words for snow, to describe different types of snow, different kinds of snow, different colors of snow, because different kind of snow responds differently. Some is good to hike on, some is horrible to walk through, some makes nice igloos in an emergency, and others do not. Some is the kind of snow that collects and forms over ice, where you might want to go fishing, and other is the sort of stuff that maybe hangs up on rocks and on barren lands. The ability to figure out what kind of snow it is could have a lot of impacts. Will I be able to compact it? Can I drive across it on a snow machine? What happens if I try to plow it and make a road? All these things are important decisions when you're in the upper northern hemisphere in the winter. And so understanding this stuff and being able to measure this stuff remotely could potentially, for example, help you plot a track of where you might want to travel or go based on the type of snow. Cloud particle size and type. So we can also do the same kind of thing, and we can look at the size of the particles of water or ice in the clouds, and so you can maybe get some idea of whether you're looking at a snowstorm or a rainstorm. whether it's a light rain or a heavy rain, little drops or big drops, tiny little bits of snow or great big flakes. All these things are possible if you understand the effects of the changes in the particle size to these various frequencies, and then simply compare them out. This one's kind of interesting. Typically students like to look at things like, for example, glaciers and how they are changing. Maybe thinking of it in terms of like global warming or something. Well, it turns out from an aerial photo it's really hard to distinguish the difference between a cloud and a glacier. But if you do it in remote sensing and you get outside of the visible range where everything just looks white, and you get up into, for example, around 1.5 micrometers, look what happens. The snow has almost no reflectance. In other words, it's going to be not white, whereas the cloud still has a significant amount of reflectance. Okay, so let's look at some other things. Apologize, but I really had to have a drink of coffee. We're looking at AVIRIS, which is a satellite that collects 50 different bands of information, and we're looking at a range here of about 2 to 2.5 micrometers. Percent reflectance along the x-axis, and we have different geologies: quartz, alunite, illite, montmorillonite, kaolinite, and buddingtonite. Now, just a little background. Montmorillonite, kaolinite, and the illite are all types of clays. And clays basically come about because of a crystalline lattice between aluminum and silica. And depending on how the lattice is structured, it forms in layers and sometimes has spaces between the layers where other elements sit, and sometimes the lattice is more or less integrated together. And so, depending on the structure of it, would give it a very different sort of response. And as you can see, there are some areas where it still gets impacted there around 2.2, and that 2.2 drop in reflectance, that's the clay absorption band. And that's how we can typically spot clays versus other things, because they'll be high before, they'll be high after, but at that range they'll be much lower, and so that gives it a very different signature than, for example, quartz. And the Landsat Thematic Mapper Band 7 also sort of covers the same kind of range, and so it should also pick that up as well. Various rocks: granites, dorites, gabbros, and olivine peridots. Peridotes, I don't know what it's called. Anyway, you can see how they have different responses as well. And we're looking here at transmission. So this is the amount of electromagnetic energy that goes through. And you can see that with some, more gets transmitted than with others at these particular wavelengths. Notice that these are very different numbers than the ones on the left, because this is probably, I would imagine, a little higher up in the spectrum. So let's look at that a little closer now. Let's look at quartz, calcite, dolomite, gypsum, and kaolinite. Quartz, you know what that is. Calcite is basically limestone. Dolomite is limestone where some of the calcium has been replaced by magnesium. Gypsum is a magnesium-based mineral, and then kaolinite is this aluminum and silicate clay. So we would anticipate that around 2.2 or so, we should have a big dip in the kaolinite for that clay absorption band. And when you get up there around 2 something, there sure enough is a dip that we don't really see in the others so much, but kind of in the gypsum, maybe a little bit. But how do we tell gypsum apart from the others? Well, if you look there at around 1.9, gypsum is much, much lower than kaolinite. So there's always places you can look. And the point isn't that you need to be able to know and memorize, what the quartz response looks across the frequency. It's to be able to look something like this up and say, if I need to differentiate between gypsum and kaolinite, where do I want to do that at? Well, you got to pick a frequency where they're dramatically far apart from one another, and then have a means of identifying both in the environment so that you can verify that what you're expecting is in fact happening. So let's look at some composite images. These are made by putting together different bands from a particular satellite. This is a 3-2-1, red, green, blue, red being band 3, green being band 2, blue being band 1, and you get an image that looks very much like this. But what happens if we change them around? If we go a 7-3-1, band 7 in this particular satellite, we now assign to red, green gets band 3, and blue gets band 1. Notice how we get a very different look. Now, what we're doing here is selecting bands that are in ranges that help us differentiate the things that we want to find differently. Okay? By doing that, it should help us to differentiate things like limestone from gypsum, from iron-stained sandstones, or white sandstones, which lack the iron. The iron would be more responsive in the red. So when we think about rocks, remember clays have that narrow spectrum of 2.2 micrometers. Limestone, gypsum have a strong blue reflectance in this current setup we're looking at. And silicates are best discriminated in the thermal frequencies. So the other thing we want to talk about is a little bit of this notion of radiometric correction. And this is figuring out how things are or need to be corrected to deal with changes in the energy from the sun. And we can do it a bunch of different ways, but I'll save you the news. The best and the easiest way is to use band ratios instead of individual bands. That way you can not have to deal with this, or you can classify the data out on each date. So the energy is constant within a classification, and then do the classifications the next day, and then compare the class data as opposed to the raw data. Lots of different ways around it. But anyway, let's look at what we have here. So here we have a digital ortho quarter quad, a DOQQ mosaic. And that means that this picture was stitched together from multiple images that were collected. And you can see that some of them were clearly during the part of the day when the sun was brighter than others. Or some were collected on days that were more overcast than others. Because the paths that the satellites take, remember, it's not like it covers, you don't always get side overlap, okay? Not like with aircraft. You get end-to-end overlap in your stereoscopic pairs, but by the time it makes the next pass, the Earth is turned around further, and there's going to be a gap between the first pass and the second pass. And so oftentimes the pass that gets the next set of images over isn't collected for a couple of weeks, depending on the satellite system. And so you can get something like this, and that's a problem, because you need all this stuff to be comparable. So what happens? Well, image values are basically how bright the particular colors are. And digital numbers are, if you were to look at the raster of that data, it would tell you what that is. It can also be a brightness value. But the thing is, they're specific to each image. And so like a value of 12 on one doesn't necessarily have the same meaning as it would on the other per se. So what determines these values? Well, the sensors. Their particular sensitivity curve, how well they respond to different frequencies. Is it an analog sensor? Is it a digital sensor? Are we converting from one to the other? Over time, these sensors, they just like the rest of us. They get older, they wear out, they drift, and they're not as accurate as what they once were. And so they're not going to always give you the same numbers. Other things that can impact these values: the atmosphere, water vapor, dust, clouds. All of these can impact some of that signal. And here's the problem: the effects are non-linear. And that means that it's not an easy math fix, it's some sort of a curved line. And with a curved thing, when you get enough of it, it blocks it completely. In other areas, it may not have that big of an impact, but the change is not a direct linear thing, and that creates problems. And they're also additive. And so, for example, water vapor blocks some, dust blocks some, clouds block some. So it's not like if one blocks it, the others don't block that part and the rest gets through. They all take their pound of flesh. And so at the end of the day, what you get or don't get is more a product of the whole than the individual parts. And some of it gets scattered, some of it gets reflected, it's partly absorbed. All kinds of things can be happening there, all of which can make these numbers change. So that's the easy parts. The hard parts are things like the solar position, the angle of the sun, the angle of the photo, the season, the time of day, where you're at on the globe, the distance between the Earth and the Sun, which is affected by the seasons. All these things impact what those numbers actually are. And then there's topography. Certain hill slopes are going to be in the sun, and some are going to be in the shade, depending on the time of day. Again, the relative slope on the ground, or the aspect where it's at in the sensor, any number of things can cause these values to become different. And that's why we have to address them. Let's talk a little bit about thermal remote sensing. So, same figure we had earlier, that's where we're going to start. We're going to look at these same kind of areas here. Particularly, we're looking at the 8 to 12 micrometer range, and that's where we're looking at the thermal infrared. We also have an atmospheric window between 3 and 5 micrometers as well. So how do we use that to our advantage? Here is some aerial photos that were collected over Yellowstone. And the first image on the left, it is a simulated natural color, red, green, and blue. Red being at 0.65 micrometers, green being at 0.55, and blue being at 0.48 micrometers. And by combining those in that order, you can kind of get this picture of what it would actually look like as a real color picture. And you see you got some fire and you got a lot of smoke, and it's hard to tell what's going on. But if we create a false color where red becomes 10 micrometers, in other words, the short wave infrared, or further out, the green becomes 2.2 micrometers. That's more like the UV. The blue, we give it a value of 1.5, which is even less. And you get this new false color setup, and what does it show you? A very different environment than what you see on the left. Now, some aspects of it you can see are probably still the same, but others are changing quite a bit. The blue appears to be the natural fires that occur on the left. The orange or the yellow looking stuff, that is the areas that are very, very hot. So they may not be in flames, but they may have already burned. So where you couldn't tell how much is burned or where it had burned because of the smoke, on the image on the right you sure can. This sort of stuff here actually has been in the news a couple of times. I think it may have went to the Supreme Court. I don't remember the particulars of the outcome. Police were trying to find people growing pot in the city, and they got thermal cameras like contractors would use to go around neighborhoods and show people, look at all the heat coming out around your windows, you need to buy the new double pane, double glass, vacuum sealed whatever windows. And they could do that. They could also ride around like this, and they could look for areas that appeared to be putting out a lot of heat, have a lot of energy that didn't make sense, and that was usually where they were finding a grow house. An example here, we have minimum insulation in the attic of the house, and you can see the top part of the roof looks red versus the rest of the house looking purple because the walls are better insulated. You also have vents and things like that near the roof, and how that could impact how things are heating up. We can use this to our advantage, even with just like aerial photography. We've got this photo of all these things. We got the library, the parking lot, and the soccer fields. And if we look at a pre-dawn thermal image, you see most of the heat that's lost is through the windows. But because this particular area is a complex facility, you see these steam lines that run underground between buildings. And they're giving off quite a bit of heat. Urban heat islands, they're a thing. Basically works like this. Cities are full of things that aren't natural. Roofs, roads, parking lots, paved, concrete surfaces, all of which absorb heat and retain it. After the sun goes down, they radiate that heat back out into the environment, making it a warmer place than what it would otherwise be. Also, there's less trees, which is sort of the natural air conditioning unit of the world. Without those there to do the evapotranspiration, and the end effect is these urban areas tend to get hotter as they're packed tighter and tighter together. And they call that the urban heat island effect. And here we can see that there's some places like buildings that are very, very hot, and some are not, like the mall, which shows up to be very cool. And this is looking at the thematic map or thermal overlay on an aerial photo to try to determine where these heat islands exist. Two photos, same place, different times of the day, looking at their thermal response. In the daytime, look at the topography and see how it affects the illumination from the sun. And look at the river. The river ends up as being blacker, showing up as to be relatively cool during the day compared to the rest of the environment. But when we go to the nighttime effect, what happens is everything else tends to cool off quicker, and where there's more water, because water has a unique ability to store thermal energy, it stays warmer longer, and so it doesn't cool down as fast as the surrounding areas. And so it stays hotter. And so the areas that you couldn't necessarily see those two rivers off to the right in the daytime become very, very obvious at night. Let's look at some other examples. Daytime, wondering what effects trees do. Looking at these thermal imagery, and you can see the trees there in the circle at the top. They're relatively cool during the day. When you get to night, they look relatively warm. And you look at the houses around, wondering where the heat is lost, and it's almost all going out the windows. So let's look at some really basic kind of imagery you could use. Satellite imagery, Landsat, and this is a standard false color composite. This looks at September 12th, 1999, approximately 10 o'clock in the morning. And a false color is going to identify different things, particularly vegetation types are going to be in the red. Things that aren't vegetation are going to be other colors. If we look at Landsat ETM mapper plus the thermal, we get this sort of a grayscale image. The colder things are, they're darker. The warmer they are, they're lighter. Again, same image we were looking at earlier, 10 o'clock in the morning. What's warm? All the paved areas. What's still cool? Where all the trees and vegetation are. Gonna map it out from a Landsat ETM and thermal to give it a different, more obvious look. We can also do thermal emissions imaging, the THEMIS. This is looking at Mars, and daytime image is dominated by the solar illumination. We see an impact crater in the early afternoon. We go back to before dawn. It shows the thermal properties, in other words, thermal inertia. What does thermal inertia mean? it means that certain elements retain heat and bleed it off at a slower rate than others. Also, we are noting here some dust-covered regions cool more rapidly because the dust is lower density, therefore it has less thermal inertia. Now, the lab you're doing this week is all about multispectral and hyperspectral, so let's just talk a little bit about multispectral thermal remote sensing. Silicate structures become depolymerized from the framework through the chain to isolated structures. Nobody cares about that. The location of the shortwave absorptions between 8 and 12 shift and get longer. Okay, so basically what they're saying is, as the structure of the minerals change, the response to the wavelengths shift. And if you know what you're looking for, you can compare it to the other things and figure out which one you have. Ocean temperatures. This is simply looking at the thermal values over the ocean and applying it to a colored scale so that you can see the hot waters of the equatorial regions and that wonderful current that keeps Great Britain and most of Northern Europe, where it should be covered in snow and just a horribly difficult place to live, having relatively nice weather, and that is because that current of warm water heading that direction brings with it warm air, which brings with it warmer weather. Here is a satellite thermal imaging from the AVHRR satellite system. We're looking here at water surface temperatures of the Great Lakes, and you can see how some lake temperatures are much, much colder than others. And why would that be? Well, could be a lot of things, but I would venture a guess is to say that a significant part of this is because of industrial development along the edge of the lake, which means there's probably power plants, which means they're probably pumping in lake water, converting that to steam to run a turbine, and then that water is coming back down into a cooling pond and going back into the lake. Or it could just be the net effect of the urban heat islands playing out somewhat on the water. Or, how about this one? It could be that some of these lakes are shallower than others, and so the water, the energy is being more fully absorbed in some places than it is in others, making it more responsive to and becoming warmer quicker. Lots of possible reasons. One of the satellites we're going to look at next week is the Aster satellites, and you can see that they have different bands that they're measuring, and that's kind of the theme too. It takes some time. I've got some videos I've got to look back up for you guys and have you to watch, because that's what we're going to do over the next couple weeks. I'm not going to do any more lecture videos. The videos I'm going to show you are of things like how to download and access Landsat imagery, Aster imagery, that kind of stuff, to show you what it is and where to get it, because it turns out all these satellites have value, but only one's going to be the best one for the thing that you're trying to do. So you got to figure out what you want to do and then figure out the satellite that works best for you. That's all I got for you guys this week. Hope you enjoyed doing the lab. We're going to get into the socket software pretty soon. We will have a take-home exam next week, and it's going to cover a whole lot of what was on this exam plus whatever you got wrong on the last one. It's going to be hard, but it is a take-home exam, so you should be able to look things up and have another opportunity to learn the things that you don't know. See you next week.